Hello everyone. Can someone confirm me whether I'm audible and the screen is visible to you?
Yes, sir.
Hello?
Yes, sir. Good morning. Good afternoon.
Yeah, okay. Good afternoon.
Good afternoon, sir.
Yeah, good afternoon. Okay, so we'll start the session for today. Today we'll discuss some problems from assignment 2. Okay. So the question number 1, okay, the question number 1 is they have given a matrix and now we have to find the norm of this matrix A, operator norm with respect to the one norms of the both Rn in the domain also in the codomain also. Okay. So first of all, how is this operator norm defined? For any operator, for the moment I call that as a T, suppose, from a vector space V to a vector space W, if T is a linear operator, then the norm of T is defined as supremum of norm of Tx, where here we take the W norm, okay, where norm of X is equals to 1, where because X is in V, we take here the V norm, okay. This is the standard definition of any norm, operator norm, okay. Here we are considering the domain. I mean the A is a matrix, so hence it is an operator from Rn to Rn. Okay, and the norms on both sides are P norms for P equals to 1 here. Okay, one norm, which is given by norm x as 1 is equals to summation of modulus of xi going from 1 to n. Okay, so this is the norm on the both sides. With respect to this norm, we want to find the norm of the matrix A. Okay. So finding it manually, what is the norm for a particular matrix is a kind of tedious job. You know, they have a certain representation of the norms, okay, with respect to the entries of the matrix. Does anyone know what is that? I mean, if Rn's are equipped with norm 1, okay, and then the operator norm of any matrix is have a certain representation. Okay, and does anyone know what representation is that? Yeah, anyone? Okay, so proceed. Here, what we can observe. See. Norm of, okay, first of all, if x I take as x1, x2, xn, suppose, then ax, for any matrix A, I write the matrix as a1 will be the first column of the matrix, a2 will be the second column. Like that, there are n columns. So this is the representation of the matrix A. Then ax will have the representation x1, a1 plus x2, a2 plus xn an. So this is only one column. Okay, this is in n cross 1 because all these AIs are in Rn. Okay, I mean AI transpose you can say. Yeah. Okay, so this is the form here. So if I want to take norm of AX, okay, this time I'm taking the one norm. Okay, the norm of AX will be like norm of summation x xi ai, right? I going from 1 to n. But with the properties of norm, this is less equal summation modulus of xi into norm of ai's. Okay, this is summation mod xi into norm of ai. Now suppose, see, these norms ais are some finitely many values for I equals to 1 to n. Like, this is just norms of each column. Okay, so I'll take the maximum of those finitely many columns, I mean the norms of finitely many columns. I call it, suppose, al. Okay, so each of this quantity, each of this norm ai is less equal, suppose I call it norm of al. Okay, so I can take it outside. This is less equal norm of al into summation modulus of xi's I going from 1 to n. But what is this quantity? This quantity is simply norm of x, one norm. Okay, so what we got is norm ax 1 is less equal norm of al, or I can write it here. Norm of al means maximum of norm ai 1 less equal I less equal n into norm x1. Okay, this is what we got. So from here we can directly observe that operator norm of a is less equal this quantity. And by the way, what is this norm ai? It is one norm of ai. So here's one norm. So this is summation modulus of a I r. Okay, I can call this as aj for the moment, just for the ease of writing. Okay, norm of aj1 I can call it as summation modulus of aij's, where I going from 1 to n. Basically, this AIs are columns, so this is like A11, A21 up till AN1. This collectively is A1. Yeah. So this collectively is A1. Similarly, here will be the second column A2. Okay, A12, A22, A32 similarly. Okay. So norm of A1 will be the summation of all columns, all entries in the first column. Okay, which I wrote here. Okay, summation of mod Aij's I going from 1 to 1 fixed G. Okay. So norm A is less equal maximum of, you take the column sum of each column, like taking the modulus of each entries in one particular column, take its summation for each column and then take the maximum. Okay, so that quantity is actually the one norm of the operator A. Okay, the matrix A. Right now we have norm A less equal that thing, but you can easily prove that norm A is equal to that thing. This, or I can write here also. So this is what we have. Okay. What we got here is norm of a matrix. One, if Rn is considered as in one norm, then any operator norm on A, so on Rn with one norm is just the maximum of column sum. Okay, modulus of column sums. Okay, is it understood? Any doubts?
No.
Yeah,
Hello,
thank you.
sir.
Yes,
How do we get this norm A is equal to? Like we have
yeah.
just proved that it is less than or equal to.
Right now
So,
it is just less than or equal to. I just left it as an exercise, but okay, we can show it also. So norm of A, we have supremum of norm of AX1, where norm x is equals to 1. Fine, we are taking supremum over all norm AX1s, where x is also from Rn, norm x equals to 1. Okay. So for the example, I just take x to be, suppose, E1. Okay. What will happen? What is AE1? AE1 will be the first column, right? E1 will be 1 0 0 0. Okay. So AE1 is the first column. So this quantity is greater or equal norm of AE1 because it's taking the supreme of over all norm 1 vectors, and E1 is the norm 1 vector. And norm of AE1 is just one norm of E1. This happens for every I. You can take E2, E3, En. So norm of A will be greater or equal summation I going from 1 to n mod Aij, which is equal to simply norm of Aj. This is happening for all j. If it's happening for all j, then it will happen for the supremum also, or taken over j. Correct? I mean, supremum
Yes.
is maximum since there are only finitely many elements. Yeah. Hence, norm A will be equal to that thing. Clear?
Okay, sir. Thank you.
Yeah. Cool. Hmm. Okay. So for right now we have this quantity now that norm of A is maximum of column sums. So now this is very easy. They have given the matrix. This matrix. We have to find its one now, right? Yeah, one now. So just find out the maximum of each column and then whatever the answer it is. Okay. So I'll leave this. Question number 2. Norm of the linear transformation given by the above matrix when considered as A. Okay, the same matrix which was given in the above question, but this time the norms are different in the domains and codomains. Both are infinity norms. Okay. So similar as the above, the first problem also, here also when the norms are in infinity norm, it has a proper structure. Okay, which is this time here it's just the row sums, like how we got the uh, the column sum, here it's the row sum. Okay, so it's completely similar. You can I mean not completely similar. You have to think a little more there, but to try this as an exercise. Maybe if not done, I'll explain it in the next tutorial session. Norm of A here will be equals to, the name is maximum over I summation over j modulus of A. Okay, which means you take the row sum modulus of each entry, then summation for every row and find the maximum. That will be the norm. Okay, so by this formula, it is now, I mean, not a big deal to find the answer of this question. So try this. If not, I will take it in the next session. Okay. This question. U be an orthogonal matrix. Consider the linear transformation U from Rn to Rn basically with two norm. The norm of this transformation is, okay. So what do you think? What is the definition you know of an orthogonal matrix? Anyone?
Inverse and transpose are same.
Yeah, inverse and transpose are same. Okay. So basically U transpose U will be identity, right?
Yes.
Yeah. So do you know any properties of this, like norm preserving properties of a matrix, of orthogonal matrices? Basically, this has this property that for any orthogonal matrix U, you have norm Ux, it's same as norm X
Economics.
for all X. Okay. So if this is happening, what can you say about the norm of U? By the definition of an operator norm we have just seen before.
So it's
So
equal to 1 then.
yeah, yeah, very good. That's the norm. So I mean, what was the definition of norm? It's just supremum of norm Ux to or norm X is 1. So, but this is just norm X, and we are taking over the supremum of all the vectors with norm 1, so it is simply 1. Okay. So this thing here was important, that it preserves norm. So if you don't know, I'll just give a quick proof of this. So because 2 norm is from an inner product, so you can write it like this. Okay, and this is actually it comes as an adjoint, but because we are in a real metric space, so it's just a transpose. Okay? But you know, U transpose U is identity. Okay, so we'll go at question number fourth. D, their diagonal matrix where the diagonal entries are given by dii equals to ai. D is okay. So you want to find the norm of a diagonal matrix. Okay, any diagonal matrix where Rn's are considered as, I mean, the two norm vectors. Okay, every vector in Rn has taken over the two norm. Yeah. Okay. So what is same formula? What will be the norm D? Supremum of all norm dx two norm over all x such that norm x2 is 1. What is dx? It is okay. We don't consider the norm for the moment. Just dx will be the column vector whose representation will be x1 a1, then x2 a2, then xn an. Okay, where x is the vector x1 x2 up to xn. Okay, this is dx. So what is the 2 norm of dx? It is square root of modulus of, okay, summation modulus of xi ai squared, I going from 1 to n, then raised to 1 by 2. Okay, so now what I'll do is each this term mod ai is there for every term. Okay, so I'll take the maximum of all those ai's and I can take it outside. So this is simply maximum of mod ai squared, then summation modulus of xi squared, I going from 1 to n, I rise from 1 to n whole raised to 1 by 2. Okay, so but this will be equals to 1 by 2 will get cancelled with this one and you are left with maximum of modulus of ai
Will be less
1
than or
raised
equal to, right?
oh sorry, yeah,
You're taking.
yeah, thank you. Yeah, so this is less equals to the maximum we have taken out outside, so now this is equal to this, and yeah, this quantity here, this is norm x. Okay, so what you have, norm dx 2 norm is less equal uh, maximum, don't, not norm ux, operator norm of d is less equal maximum of modulus of ai 1 less equal I less equal n. Okay, so now you have less equal, but similarly if you take in place of x you take ei suppose, then you get greater equal also. So norm d will be equal to maximum of modulus of ai is 1 less equal I less equal n. Okay, is it fine? So the option number 1 is correct. Anyone, if he has any doubts, you can ask. Okay, okay. We'll go to question number 5th. A belongs to Mn over R. Define linear transformation A from Rn2 with Rn2. Which of the following are true? Okay. So if A is defined from Rn with 2 norm to Rn with 2 norm, what do you know about norm A? It is supremum of norm Ax to norm such that norm x equals to 1, right? But it has another representation also. Supremum over all x belongs to capital, I mean Rn actually here. Rn where x is not equal to 0, you take norm Ax divided by norm x. Okay, this is the formula for norm A, another representation. You can prove that both representations are the exact same. So if you take the square on both sides, norm Ax to square, but the two norm on Rn, it comes from an inner product, right? Our usual inner product, we know that. So this is simply supremum, same thing. And here it is inner product of Ax with Ax divided by inner product of x with x, which is simply supremum of inner product is x transpose A transpose Ax, because the standard inner product in Rn is inner product of x with y is equals to y transpose x. Hence we have here this and here x transpose x as mentioned in the option number 1. Okay, the first is right. So second, what does second say? If B is any matrix and P is an invertible matrix and A equals to P inverse BP, then norm A and norm B are same. What do you think about this? Is it true? So basically, what do you call this A and B matrices if there is such a relation in between A and B? Like if there is a P such that A equals to P inverse BP, then you call those two something. Do you know what is the relation between A and B here? Anyone? Yeah, yeah. So this is similar matrices, A
Similar
and B.
matrix.
Yeah, yeah, correct. So what this second option is saying is for the similar matrices, norms are same. That's the second option saying. Okay. So this is not true. You can find an example, actually in the example in R2 you can think of. It's easy. Such that you find matrices A, B, and P, such that A equals to P inverse BP, but norms are not same. Okay, you can for the hint you can think of maybe the projection operators, not projection operators, but okay, I'll just give you one hint. Think about this matrix. Suppose what does this do for any x? X1 x1, right? Which means 10 point has been mapped to 11, right? But if you think in the terms of norms, norm of this guy is 1 here, but this guy has norm √2. Okay, so it kind of uh, projecting the vector on the your y equals to x subspace, but scaling it also at the same time with the √2, the norm, scaling its norm with the √2 also. Okay, so if you try to find the matrix P, there are matrix P such that it doesn't scale, then the norms will be different, but there will be a similarity between the two matrices. Okay, you can think of any examples actually. This is just one direction. Okay,
Sir, can we prove it without contradiction? Like with this example, we are proving by contradiction, right?
no, we are not proving something. We are disproving that thing. option B.
Yeah, so you said we can take some examples and then disprove that this option is wrong, right?
Yeah, yeah.
So can we not prove it?
It is not true, no. So how can you prove it?
No, so I was asking, can we not prove that it is not true? Like without taking specific examples,
Mhm.
I'm not able to think of any specific examples that doesn't satisfy this. So is there
Okay, so
any?
you want to give a proof that the statement is wrong.
Uh,
I don't know. Maybe you can try, but this is the general way of going. If you see a statement which is wrong, you try to think of a counter example which will prove that this is wrong. Okay. I
okay.
don't, I don't know any theory to prove a wrong statement.
No, here the doubt is how to choose the correct example. If
How to?
not, we have to go for the contradiction. So that's what I think she was aiming.
Yeah, yeah.
Oh no, I don't
Yeah.
understand.
No,
Okay, oh,
see,
counter by
yeah, yeah,
contradiction you want to
yeah,
prove. Okay, so you want to assume that
yeah,
if
yeah.
okay, so you want to assume that the norm A will be norm same as norm B for any invertible P matrix, and then you will arrive at some contradiction.
Yes, yes,
Yes.
exactly.
Okay.
Method of
Thank you.
contradiction. Yeah, that also is possible. You can do that. Do
Okay.
that. Maybe I'll also try, and I'll see when what contradiction I'll get. Maybe for the next session we can discuss that. Okay.
Sure, sure. Thank you, sir.
Sure, sure. Good. I'll also try the way of contradiction for the option number B, and then we can see in the next session. Okay. So option C. Okay. So are you getting any disturbance? I mean, some other sound from the background?
Very mild, very mild.
Okay, just a minute. I'll close this window. Now is it okay?
Yeah, good.
Thank you. Okay, so B is not correct. Go for C. C is saying if O is an orthogonal, right? Yeah, O is an orthogonal matrix, and same thing happens, then does it preserve the norm? Okay, so see, for the both norm A, definition of norm is supremum of all norm X, where norm X is 1. Similarly, for norm B, or I can refer here as Y. I mean, they are not same, but okay. So I want to prove that these two numbers are same, like supremum of certain elements here is same as supremum of certain elements here, kind of two sets, and I'm claiming that if possible, the supremum of these two sets are same. Okay, that's the claim. So if I show that the two sets are same, then it clearly satisfies, right? The supremum is also same. Okay, so just think about this, that if I make this set as suppose A tilde, call it, to be the set of all norm AX, where norm X2 is 1, belongs to, and I call B tilde to be set of all on By. Y belongs to Rn. So my claim is that these two sets are same. Okay. So if I prove that, I am done. Okay. So let's take one element. Suppose x belongs to Rn such that norm x2 equals to 1. Okay. So the claim for the moment is find an element y belongs to Rn with norm y is 1 and norm of ax2 is same as norm of by2. Okay, if this claim is satisfied, then a tilde will be contained in b tilde. Okay. Okay, so what will be the y? See, so A is, first of all, we have A transpose B, sorry, O transpose B O. Okay, this we have. Okay, yeah. So what is AX? AX equals to O transpose B X. Okay, so I'll call this OX as Y. Okay, and let's see if this Y satisfies what we want. For me, Y is OX. Okay, so now what is the norm of this Y? Is it 1?
It's equal to norm x.
Yeah, it's equals to norm x. Yeah, that's correct. And we are taking the x we are starting with is of norm 1, so norm y will be 1. Okay, because the O is orthogonal matrix here. So first condition is satisfied that we found a y belongs to Rn, so the norm y2 is 1. So if this happens, we want to see. Okay, so norm Ax is now same as norm of O transpose By. Okay, so now since O is orthogonal, O transpose will also be orthogonal, right? So this will be same as norm of By. Consider this By as an input for O transpose. Norm Ax equals to norm By. Done. We got for each x belongs to Rn with norm x2 is 1. We found an element y belongs to Rn with norm y2 is 1. So that norm ax2 is equals to norm by2, which implies a tilde is contained in b tilde. Okay. Now the reverse what we have to do. Now let suppose y belongs to Rn with norm y is 1. Okay. So claim is find x belongs to Rn with norm x2 is 1 such that norm of ax is same as norm of by. Okay. Okay. So since O is an orthogonal mapping, okay. So we know orthogonal is an onto mapping. So there exists some x belongs to Rn such that O x is equals to y. Like the inverse image of y I am taking under the operator O. Okay. So the claim is this x can work. Right now the direction is this x can do what we want. So for the moment this x also has norm 1 because of the same orthogonal property of matrix O. Norm x is 1, and what will be the norm of Ax here? Which is norm of O transpose B Ox, which is same as norm of O transpose B Ox is y. and since O transpose is orthogonal, this is same as norm of Y. So simple proof, nothing much involved. Now the two sets, now this will imply B tilde is contained in A tilde. So from 1 and 2 I have A tilde is same as B tilde, which implies these two sets are same, these two sets, and the norm A is just supremum of A tilde, simply, I mean, over the elements of A tilde, and norm B is just supremum of elements of B tilde. So if the two sets are same, their supremums are also same. Okay, any doubts in this? Anyone can just tell me. Okay. So just as a remark, that will be useful also again. Here, what we have observed is O is same. Okay, O transpose BO, right? So the remark is even if A equals to, you can, if suppose you can write A equals to U, B and V. Okay, where U and V both, okay, there is no difference in U and V. U and V both orthogonal, then by the similar procedure you can show that norm A will be same as norm B. Okay, I mean, try to prove it. This will be useful in further questions. Okay. Yeah, next, this question number 6, the immediate use of the remark I have mentioned before. So A is an mapping from R3 with 2 norm to R3 with 2 norm, given by real symmetric matrix with eigenvalues of R1 root 3 root 5. What is the value of norm A? So we don't know any matrix here. Okay, we just know the eigenvalues of that matrix. But what the additional condition we know is the matrix is real symmetrical. How can we use this real symmetric matrix? Anyone? Any clue?
We can diagonalize it.
Yeah, cool. Yeah, not just diagonalize. We know something more. I mean, see, you're correct. Diagonalizing is absolutely correct. But in the previous question, you observe this thing, option number B. Okay, here, if suppose this,
Then A here, yeah. So P inverse BP will be diagonalized of form of B, right? I mean,
yeah, if B is the
B
diagonal
real
matrix
BP.
here, then P inverse B DP will be the diagonalized form of A. I mean,
Diagonalized form of B.
sorry.
P inverse BP will be the diagonalized form of B, right?
Okay, the thing is, what I'm saying is, if suppose in place of B here in option B, there is a
Yeah.
diagonal matrix. Okay,
Uh,
that
okay.
we say as a diagonalization of A, right? I mean, what is the diagonalization of A? There exists a diagonal matrix D such that A equals to P inverse DP, right? For a invertible P matrix. This is diagonalization of A, correct?
Yes. Okay.
Yes, sir.
Yeah. So if you just diagonalize, what is the use of it? I mean, in the option B says that these two are not did not be same, right? Like in place of B, if you want to show, like if there is any use of this what do you say, property, that you have to relate a matrix norm with its diagonalized matrix norm, then this representation is not going to help, right? Because for any invertible matrix P, this is not true, that the norms are same, correct? There are some special invertible matrices. For example, not for example, can you see, as you see in option number C, orthogonal matrices. If in place of P there is an orthogonal matrix, then the norms are same. Okay.
So the eigenvectors, they are orthogonal to each other for the real symmetric. So that will be useful here.
Yes, yes, absolutely. Actually, the higher thing is the spectral theorem. I mean, you call this thing as uh, you call this eigenvectors being diagonalizable, or in other words, a real symmetric matrix is unitarily diagonalizable. We say that. Okay, that means, all right.
What do we mean by unitarily? Actually, I'm not from the mathematics department, so
Cool, cool, cool. So, see, unitary means the matrix, the orthogonal matrix we know what is U transpose U equals to identity, right? This is
yes,
for real case. Hmm?
yes.
But if you consider the matrices with complex entries, we take the complex conjugate there. In place of transpose, you write U star. Okay. So
Okay,
if this happens, then we say U to be a unitary matrix.
okay,
Okay. So
yes.
a matrix A is said to be unitarily diagonalizable if there exists unitary matrix U such that A equal also a diagonal matrix T and diagonal matrix D such that A equals to U D or U D U star. Okay. So if this happens, then you say that the matrix A is unitarily diagonalizable. Okay. In the real case, it is orthogonal diagonalizable, you can say, where because the unitary matrix is same as the orthogonal matrix in real case. Okay, is it clear to you?
Yes, yes.
So the theorem is, there is a big theorem in linear algebra which is called as the spectral theorem. Okay, that says every normal matrix in complex plane is unitarily diagonalizable. Okay, so when a special condition of that theorem is just in real case, every real symmetric matrix is unitarily diagonalizable. That means if A is real symmetric, then there exists U orthogonal such that A equals to U D. Okay, same U transpose U D, you can say U transpose D U. Okay, where D is diagonal. Okay, so on the diagonal entries of the matrix D will be the eigenvalues. Okay, so here the eigenvalues are 1 root 3 root 5. So some questions before we have seen that if there is the diagonal matrix, then what will be the norm of the diagonal matrix? Like if we just consider D to be this matrix 1 root 3 root 5, the two norm of the matrix D will be, we have just saw some time before, that it will be
Sum
the,
of mod of these entries.
no, two norm, this is a two norm.
Oh, is it under root of square
Yeah, I mean
sum
two
of
norm is that with respect to that the diagonal matrix norm was just maximum of the diagonal entries.
Maximum matrix of diagonal matrix.
Yeah, yeah. Okay. So now at the moment only thing I know is the norm of this D is root 5. Okay, two norm. But the previous remark I have mentioned that with this condition you have norm A is same as norm D. Okay. Also the previous question says. for an orthogonal matrix O and A equals to B O transpose BO, then norm A is norm B. Here in place of B, we have a diagonal matrix D. So norm A is same as norm D, which is root phi. So that's the answer. Just using the past questions. Okay. So we'll go next. Yeah. So which of the following statements are true? So question number 7. So the first part. So the claim here is actually norm x for any x belongs to Rn or maybe infinite also. Norm x2 is always less equal norm x1 for all x belongs to L1. Okay. So this L1 space is tuple spaces. I mean, it can be infinite also, it can be finite also. It depends. L1 of natural numbers is sequence space in with the norm 1, and L1 n when you write it means it is from Rn. It is just Rn with norm 1. Okay. So I'll just first explain for Rn why norm x2 is less equal norm x1 for all x belongs to Rn. So what will be one norm? It will be summation of mod xi, right? Or I'll modulus of x1 plus modulus of x2 plus modulus of xn. So if I square it on both sides, okay. So you know this inequality which is always true. For example, x1 plus, I mean, if a and b are positive, suppose, then a plus b whole squared is always greater or equal a squared plus b squared, right? Because there will be an addition term there, which is 2ab. Correct. So the same thing applies for all n's also. Okay. So mod x1 plus mod x2 up to mod xn squared is less equal mod x1 squared plus mod x2 squared plus mod xn squared. But there's nothing now because if you are taking the square of the whole thing, no, there will be some additional term inside. 2 times mod x1, x2, 2 times mod x1, x3 similarly, then triple products, four products and all, which are all positive. Okay. Oh, I reversed the inequality. This will be greater or equal this. Okay. And now what is this thing? This is just norm x 2 norm squared. So we're done. So 2 norm of any x is less equal 1 norm of any x. X belongs to Rn. Okay. This is for finite dimensional cases. So for infinite dimensional cases also, what you do is, since it is true for every finite dimension, for every n, right? This is true. So you take the for any x belongs to suppose L1 of natural numbers, which means it's a infinite sequence. You define like Sn, which is Xn, truncate, and yeah. So now this inequality norm Sn, you can call it Snx, maybe some notation. It's just you have to first you have to understand the main concept here. Notations we can adjust somehow. So we know norm Snx 2 norm is less equal Sn x 1 norm, right? This is happening for all n. So you take the limit and going to infinity, this Sn becomes the your x, and since it is already in L1, so the sum is also finite. The sequence of partial sum converges somewhere, hence the inequality will also be preserved. Okay, so you can try this. This is not a hard part. Okay. Question number 8. So everyone understood, right? The last one, or anyone having any doubt? Oh, it's not done completely. I'm sorry. So question number 7a is true because we have norm x 2 norm is less equal norm x1, and which is given to be less equal 1. Hence norm x2 is ultimately less equal 1. Okay, but the second one is not true, that 2 norm of x is less equal 1 norm of x. We can give example basically. You can think of any examples. Can anyone think of an example from maybe finite dimensional space Rn? Immediate example. Oh wait, oh wait, this is true. I'm sorry, I misread it as norm x1 is less equal norm x2. So this we have proved just now. Norm x2 is less equal norm x1 for every x belongs to L. Yeah, this is true. For third one, the norms are equivalent. For that, you have to show something. These norms are not equivalent. Yeah. So now, anyone having idea how to think about the option number C, norm equivalence? So when they are talking about norm equivalence, first of all, we are dealing in infinite dimensional space, okay, like L1 or natural numbers. Because for finite dimensional space, every norm is equivalent.
So can we show that do not exist any constant m such that the one norm is less than that constant times the two norm?
Yeah, yeah, yeah.
So that
That's basically it. That's the idea. Correct. So the claim is show there does not exist a constant C, take for the moment positive, such that one norm is less equal C times two norm. Right? This is what you were saying, right?
yes, yes.
I mean, this should happen for all x. Yeah, so that's absolutely correct. We have to show that there does not exist any C. Okay. So we'll go by contradiction. Suppose there exists C such that norm x1 is less equal C times norm x2 for all x belongs to L1. Okay. So I'll try to find some elements xi's which whose norms are unbounded, or I don't know, it goes infinity or something. Okay. Hmm. So what about this? Consider xn. I mean, now this time xn is a sequence of sequences. Okay. So I mean, what I mean by that is this is x n of 1, then x n of 2, x n of 3, like this. Okay. So I'm trying to create an example for this contradiction. Okay. Let's see how it goes. Defined as xn is this is 1, then 1 by 2, then 1 by 3 up till 1 by n and then 0. Correct? So does this belongs to L1? That's the question first. Question is, does xn belongs to L1 for every n belongs to natural number? Is it? Is it true? Anyone? So what is mean by belonging to L1? Belonging to L1 means if you consider any sequence, suppose x is this sequence x at 1, x at 2, like this for infinity. So x belongs to L1 means summation modulus of xj, j going from 1 to infinity is finite. I mean the absolutely summable sequences, say simply. The L1 is just the set of all absolutely summable sequences. So is this sequence like xn is absolutely summable? That's the question.
Yes.
Yes, right? Because they're just finite limited non-zero terms. After a finite stage, everything is zero. So for
Yes.
every n, xn is in L1. Right? So what will be the norm of xn? One norm. Okay, precisely. One norm of xn is summation 1 by j going from 1 to n. Right? So this is in nothing but a sequence of partial sum Sn, yeah, of the series this summation 1 by n series, right? And going from 1 to infinity. Okay, we just think about this series, then it is just sequence of partial sums, right, of this series. And you know that this series diverges. Yeah, you know this series diverges. So according to our theory, if there exists a C, then what we should have is norm of xn should be less equal C times what do you say, norm xn 2 norm, right? But what is norm xn 2 norm? It is summation 1 by j squared, j going from 1 to n. And this is sequence of partial sum for the series summation 1 by n squared, correct? But this series is convergent. You know there is some finite some fixed value where this series converges, right? So this is less equal, what do you say, some m, maybe m is the value of this series, correct? So you got this c times m, correct? Anyone have any doubts? No doubt. Okay. So what we got is, if you just observe here carefully, that this sequence of partial sums of this series 1 by n is bounded from here, right? C is a fixed constant, m is the fixed constant, so this Sn became bounded, but this is the contradiction because Sn has to be unbounded in order to this series to become divergent. Sn has to be unbounded, right? So that's the contradiction. There cannot exist a C such that norm x is less equal, norm x1 is less equal C times norm x2. Contradiction. Okay, understood? Okay. Hmm. So question number 8 now. So 8 is the function spaces. Okay. We have capital VP with the C01 equipped with the P norm, and the values of P are just 1 and 2 we are taking. We have to check whether the identity map is continuous from V1 to V2 or V2 to V1 or it's an isomorphism. Okay. So we'll check the first option. What do you want to check is, does the identity map from V1 to V2 continuous? That's the question. Any guesses? Or anyone, if anyone tried, what's the answer or something?
We can show with the norm inequality, norm in V2 is less than or equal to norm in V1 then.
Yeah. Correct. So basically, this continuous means bounded. This because it's a linear operator. So yeah, you are correct. If we can show, if this happen, that norm x to norm is less equal x one norm for all x belongs to C0 and x means now this is a function. Okay, I should write f here, but it's fine. Okay. Okay, if this happens, not just less equal, some c times suppose, then done. Right? So what is norm f2? It's integral 0 to 1 modulus of ft squared dt raised to 1 by 2. And norm f1 is simply integral 0 to 1 modulus of ft dt. Okay. So anyone know Holder's inequality? Holder's inequality simply says that integral from 0 to 1 f into g mod dt is less equal p norm of f into q norm of g. Okay. But in our case, or you take p equals to 2 suppose, then this will be same. Where yeah, p and q had the property that they are complex exponents of each other, which means 1 by p plus 1 by q has to be 1. Okay. So if I take 1 norm modulus of ft, and I can write here as a constant 1. Okay. Okay, it's fine. Now, a constant 1 means now I'm treating that g to be a constant 1 function. So by Holder's inequality, I have this to be less equal norm f2 norm and then constant function 1's 2 norm. But what will be this? Integral 0 to 1 dx, which is simply 1. Correct. So you directly got that 1 norm of any function f is less equal 2 norm of f, which means if you consider the identity function I from v2 to v1, then will it be continuous now?
Yes.
Yes, it will be continuous. So what we got is from V2 to V1 it's continuous right now only. Okay. So what we got is from V2 to V1 is continuous. How about V1 to V2? Actually they are not, it's not continuous from V1 to V2. You can think of a counter example I can give you actually for the moment. So as you said, if I want to show that it is not continuous, what I'll show, there does not exist any C such that norm of f 2 norm is less equal C times f1 norm for all f belongs to C01. Right? If I show this, I'm done. That v1 to v2, the identity map will not be continuous. Okay. If suppose there exists a C with this property. Okay. Now we construct some family of functions which will give us the contradiction. So try to think in this way. This okay, wait. This is one, this line, and this is half, this is two. You just I mean don't uh, care about the scalings. I mean since this much distance is one now and this is only one, but you just assume it. This function and afterwards it's zero. So this function is suppose f1. I call it as f1. This function I call it as f2. Now again above, suppose you have 3 here and you go for 1/3 here, then you connect these two and then you go 0 forward. You can see these functions are all continuous, right? All functions are continuous, you can see. Basically what I'm doing is fn at t, okay, what will be the equation of those functions? See, what I'm doing from n, right? From n starts from n and ends at 1 by n. It's just a straight line, right? So how you represent equation of straight line? 1 minus lambda times what is the point here will be 0 comma n plus lambda times 1 by n comma 0, right? Which will be lambda by n comma n times 1 minus lambda. Correct? Yeah. So what will be the equation of this line from just connecting the points n comma 0? No, sorry. Connecting the points 0 comma n to 1 by n comma 0. The equation will be y equals to n times 1 minus nx. Okay, you can observe from here. So basically how the functions are defined are fn at x equals to n times 1 minus nx when the 0 is less equal x is less equal 1 by n. See the line statement till point 1 by n, other than that 0. Okay, so everyone understood the construction, like how the functions are constructed? Any doubt? If any doubt is there in the construction or something, you can ask. Okay, if no doubt, I'll proceed. Yeah. So these are six functions, and what will be the norm of this function? One norm will be just integral 0 to 1. Now, since after 1 by n everything is 0, so I don't have to care about those. 0 to 1 by n only, modulus of fnt dt, right? But We can directly see one norm is just what? Integral only, no? So integral is what? Area under the curve for every function, right? If you observe carefully, for each of these functions, these are just making a triangular shapes from n to 1 by, right? See this shape for f2, this. What will be the area? Half times base. For every triangle, base has 1 by n and height will be n, right? What is this? Half, right? Which means fn1 is equals to half for all if all n belongs to natural number simply, right? So, but what is fn2 squared? I'll consider it will be 0 to 1 by n modulus of fn x squared dx, which is 0 to 1 by n. Fn x is n times 1 minus nx squared dx, which is equals to n squared. Now 1 minus nx squared is 1 minus 2 times nx plus n squared x squared dx, which is n squared times x minus n x squared plus n squared x cubed by 3 going from 0 to 1 by n. This is n squared times 1 by n minus this is 1 by n plus 1 by 3n, which is equals to n by 3. Okay, so what do you got? See here carefully. We got that. Okay, first of all, we had assumed that there exists a C. Okay, with this condition that norm f2 is less equal to C times norm f1 for every f belongs to C01. But then we got a function. We got a family of functions with the property that norm of fn2 norm is n by 3, which will be less equal C times norm fn1, which is C by 2. This should happen for all n belongs to natural number. You can see a straight away contradiction here. I mean, natural numbers are going infinity. They cannot be bounded by one fixed number, right? So we got a contradiction here. So this cannot happen. That identity mapping from V1 to V2 can't be continuous. I mean, is not continuous actually. Yeah. So since only one-sided mapping is continuous and not the other side, the identity mapping is not a not a isomorphism there. This gives you the answer to question number 1 and sorry, question number 8, option 1 and option 3rd also. Is it clear the whole construction and norm thing for option number 8? Okay. Okay, then we go with question number 9. Okay. Define the linear operator T and S. Just a minute. Yeah, okay. So they have defined the two linear operators T and S. This Tx is, don't confuse it with indexed operators. Okay, this is just T of x, and this is just S of x. It's the right shift operator, and one is the left shift operator. So you can see directly ST will be identity because first of all T is shifting to the right and then S is shifting to the left. So you will get the as it is element. Okay, so ST will be identity. Second option is T and S are invertible. Okay. So what do you think? Any ideas? Have anyone seen these operators before? Okay, even if not seen, you can uh, observe here. No, invertible means what? You need one bijection. I mean, it has to be a one and onto. Okay, so is the operator T onto?
Yes.
What you're saying? T is an onto operator.
Yes.
Okay, what will be the image of E1? I mean, 1000 all zero. Do you have any pre-image for that?
So then T of X will be 0, 1, 0, 0, 0.
Yeah,
Oh,
no, no. Onto means for every element in the codomain,
mm,
you need to have an
yes.
image in, right? So if you take
Yes.
in codomain, suppose y equals to 1000,
Okay.
so does there exist an x
No,
in
no, no.
L1 such that tx is equals to y?
No.
No, right?
No.
Which implies t is not onto and s. Okay, s will be onto, but s is not 1, 1. Okay. Can you give me an element in the null space of s? Null space of S means
So any X and then 0, 0, 0 will.
any yeah, correct.
Mm,
First element any non-zero and all other zero will give to zero. So
yes.
both T and S won't be are not be invertible. So the option C is calculative only, not a big deal. You can calculate that the both norms are same. I left it leave it as an exercise. No big deal. I mean, if it becomes any hard or something, you tell me in the next session. I will discuss this. Both the norms will be same, but there will be a difference, okay, in the two norms. When you try to solve, you observe this difference. One norm will be attained, okay, that there will be an element x such that norm of one operator will be same as norm of sx or tx, okay, which one attains you see it, but one is unattainable, okay, there cannot exist one x such that norm equals to image of norm of the image of an operator. So there is this the difference here. You try to prove this first and then observe the difference. Okay. So, yeah. So question number 10. They have given a point p equals to 0, 0 and h to be set of all x, y such that x square, so x into y greater equal 1, which means this parabola here. Okay. The region is this region. Okay. If R2 is product of the usual Euclidean norm 2 now, what is the value of distance of the point P with the set H? Okay. So distance means the smallest distance when we say. Okay, like the smallest distance of 0, 0, this point with this set. That means, if you can see, if I join this point with any point in the set, this length is the distance, right? So by, like visually also you can see which will be the shortest along the line y equal to x, right? Correct? Because for any other line, if you go, it will give you the, I mean, large length. Okay, just by observation, but we'll give a concrete proof also. But by observing, you can say that, right?
Sir, can you please repeat what you said?
See, distance of P from H will be what? Infimum of, norm of P minus X. Okay, I mean X means now. Okay, just 0 minus XY, where X Y greater or equal to 1 means what? X Y belongs to H actually. So what is this? Infimum of norm of xy itself. Okay, so what is the norm of xy? 2 norm of xy, square root of x square plus y square. Correct. So what is this quantity? This is just length of every point in that set, right? So any point if you consider in the set, so square root of x square plus y square is this length, right? For any point, this length, right? We have to minimize that length, right? So if you observe which point has the minimum length, like you see these lines, if you go other than this y equals to x line anywhere, the length will be increased, right?
Yes, yes.
Yeah. So by visually you can imagine that this point here 1 1 is the point which will give you the minimum distance, right? So norm of that point 1 1 will be what? Square root of 2, right? So answer is going to be root 2, but we'll give some proof here. Okay. So what we have to minimize this thing, right? Square root of x square plus y square, right? But what we know already is x square plus y square is greater or equal 2 times xy, right? By basic x minus y whole square thing, right? This we know always. And for our set, what x into y is greater or equal 1. So this is greater or equal 2, right? So the lower bound of square root of x square plus y square is root 2, right? It can be less than that. So what will be the infimum? If you can get a point in the set whose value will be root 2, then that's the infimum, right? So you just take this point 1 comma 1. It belongs to H, and square root of 1 squared plus 1 squared is root 2, right? So it implies distance of P with H is root 2. Okay, understood?
Yes, sir.
Yes, sir.
Yeah. So with this, the assignment 2 is finished. Stop the presentation. And so anyone has if any doubt they can ask.